All right, good morning, everybody. So we were talking about interfaces at the end of the last lecture. So remember what an interface is in Java? An interface is just it's basically a set of methods, right? And so typically the methods have no implementation, right? A class that implements an interface must provide the methods that are in the interface. What an interface lets you do is it lets you specify a common set of methods that you know all classes implementing the interface must have. So for example, you can create an interface called sort, right? Every sort has a method inside of it, also called sort, that takes in a list. Presumably the sort method sorts the list. Excuse me. What you can do from there is you can create a class called, say, insertion sort, right? And the insertion sort implements the method sort, right? Where the sort method implements the insertion sort algorithm. You can have a different class called merge sort that provides a sort method that implements the merge sort algorithm, right? And so on and so on and so forth. Because you used an interface back here, right, what you can do is you can write a method that takes in an object of type sort, right? And that object must provide that object can be either can be an insertion sort object, it can be a merge sort object, or any other object that implements the interface. Right? The user now has the freedom to pass in whatever object they want, as long as it implements the sorting interface. Right? So in the Java standard library, the interfaces show up all over the place. Right? So comparable is one of the interfaces that we saw earlier in the course, right? So remember, comparable is the interface that lets you compare two objects for order, right? And so what that lets you do is it lets you write methods, right, that require comparable objects, right? So for example, back in sort, right, you might require all of your objects in list, or your element types in list, sorry, to be sortable, right? In other words, there is a way to specify that whatever element type is in the list, they must be comparable, right? And we'll look at that later on in the course. Okay, so for today, we want to implement what's called the Iterator interface. We want to look at the Iterator interface. We want to create a class that implements the Iterator interface. All right, so when you write a for each loop in Java, what's actually happening is there's an object of type iterator that gets created. Right? So an iterator is an object that knows how to iterate over a collection of elements or over a sequence of values. Right? So every list is able to provide an iterator object. You can use that object to look at all the elements in the list. So when you write a for each loop that runs over a list, right, the list is actually making you an iterator object, and the compiler is using that object to visit every element in the list. Right? The same is true for sets, right, and for maps. Right? So if you have a map that so in the map you have an iterator over the key set, and you also have it's also possible to iterate over the values. So the interface is pretty straightforward for iterator. Right? So this is the Iterator interface. It's copied directly from the Java standard library. Right? So for the time being, all that we care about in Iterator is that it has two methods. It has a method called hasNext, and it has a method called next. Right? HasNext returns true if the iterator has more elements in the sequence to look at. Right? Next returns the next element in the sequence to look at. If you have an object whose class implements the iterable interface, that lets that object be the target of a for each loop. So notice that the name of the interface, there's a different interface. So there's a second interface called Iterable, right? So iterator, it's the interface that defines an object that can iterate over a sequence. Iterable is the interface that says you can Iterable is the interface that says you can iterate over a sequence, right? So the iterator is the thing that knows how to iterate over the sequence. Iterable is the thing that says you can iterate over the sequence. if you look at the list interface says it implements the collection interface and the iterable interface. Right? Similarly, set says it implements the collection interface and the iterable interface. Right? So you can see here that a interface or a class can implement multiple different interfaces. Right? So a class or an interface can implement as many interfaces as you want. You might remember that in an array, you can also write a for each loop. Right? It's a quirk of the language that arrays don't implement iterable. The language pretends that it does, but it doesn't actually implement iterable. Right? Okay, so remember iterable, that's the interface that lets you iterate over a sequence. All that it does is it provides an iterator method. Right? The iterator is the thing that knows how to iterate over the sequence. Right? So in Python, you can write a loop, well, the only type of Python loop that you can write is a for each loop. Right? So for every Python loop is always, every Python for loop is always for something in something else. Right? And so if you want a counting style loop in Python, you iterate over a range like that. Right? If you want a counting style loop in Java, you write a standard Java for loop. Right? For int I equals 0, I is less than 10, I plus plus. Now, if you really like the Python syntax of writing a for loop, you can actually do this in Java. You just have to make your own class that represents a range, right? And then have range implement iterable, right? And so in Java, if you really wanted to do this, you could write something like for int I, right, in a new range from 0 to 10, right? Syntax is slightly different, right? But looks closer to Python than the regular counting style for loop in Java. That's from a previous version of the class. So you didn't actually see range in assignment 3 this year. Okay, so all right, so you can make a class that represents a range of numbers. Right? So to do this, you make a class called range. I want a range to be a target of a for each loop. So I can say that it implements iterable. Right? Now this thing, when it counts, it's going to count as it's going to count using integers. Right? So it's iterable over integers. Right? So iterable is also a generic type. So you have to specify the type here. Right? So by saying that a range implements iterable integer, we're saying that a range is counting over some integer values here. Okay, so what do you need to define a range? Right? So I need a starting value, and I need a stopping value. Right? Notice the stopping value is not part of the range. Right? So the range 0 to 10 is the numbers 0 through 9. Right? So I need a starting value, and I need a stopping value for my range. So there are my two fields. Right? Now you can provide as many constructors as you want. So I'm going to provide two. I'm going to provide a constructor where you specify the stopping value. Right? So if you only specify the stopping value, that counts from 0 up to the stopping value. Right? So here I'm going to chain to the next constructor. Right? The next constructor, you specify both the start and the stop value. Right? And it looks like the stop value, the starting value has to be, the starting value cannot be greater than the stopping value. Right? So start is always less than or equal to stop. So this constructor sets this start and this stop to start and stop. Right? So back here, it would set start to 0 and stop to 10. Right? Now, sorry, back up here. Right? We want the range class to implement the interable interface. Right? So remember what that means. Go back to the interable interface. Right? It says you must provide a method that returns an iterator object. Right? So we provide a method called iterator. Right? It returns an iterator over integer object. Right? Now the question is where does this iterator object come from? Right? And the answer is we have to make one ourselves. Right? And so we're going to make another class called range iterator. right? And so a range iterator, that's an object that knows how to count from start up to but not including stop, right? That's all it does, right? It just counts from start to stop. Right? So it's not, conceptually, it's not going to be difficult to implement. Right? Okay, so now the question is, well, where do I put this class? Right? And so the answer is, you could put it inside of a separate class, right? So make your own range iterator class, right? And put it, implement it like we would normally do. Right? In this case, I'm going to place the range iterator class inside of the range class. Right? Now, the reason I'm going to do this is because no one actually ever needs a range iterator object directly. Right? All people care about, all the users care about are ranges. Right? They don't actually need an iterator over the range. Right? So I'm going to make it private so nobody has access to this class except for the range class itself. Right? And so this is the first time we've seen a class defined inside of another class. Right? And so this is what's called a nested inner class, right? Or just inner class in Java. Right? By making it private, only range objects can actually make one of these iterator objects. Okay, our iterator needs to implement the iterator interface. Right. All right, so this is the first instance of a nested class that we've seen. Right. So a nested class is simply a class that's defined inside of another class. Right? So range iterator is defined inside of range. The reason you do this is because a nested class usually only exists to serve the class that it's defined in. Right? So range iterator is really only useful inside of the range class itself. Right? There's no reason anybody would want a range iterator object just on its own. Right? You need a range to iterate over as well. Right? So the purpose of range iterator, right, is to serve the range class that it's defined in. Right? Now normally, so if your nested class would be useful on its own, then you should just make it a normal top level class. Right? So for example, if it would actually be useful to have a range iterator object without a range, right, you would make a range iterator class outside of range. Right? But it's not, right? The only purpose of a range iterator is to iterate over a range. Right? So you need a range object for a range iterator object to work. Okay, so iterators are normally defined inside of a nested class. Sorry, iterators are normally defined as a nested class because you can't have an iterator, without the enclosing class. Right? So it doesn't make sense to have a list iterator if you don't have a list. It doesn't make sense to have a range iterator if you don't have a range. Right? So in this case, it really does make sense to put the iterator class inside of range itself. All right, so there's another distinction in Java that you need to know about. You can have what's called a static class. Right? So it is possible to mark a class as static. Right? Notice that ours is not. Right? So this is just private class. Right? So a nested class is an inner class if the class is not marked as being static. Later on, you're going to see what a static nested class is. Right? For now, this is a nested inner class. Okay, so objects of an inner class type always have reference to an object of the enclosing class. Right? So what does that mean? Right? If you look at that sentence on its own, that seems kind of confusing. All that means is that, right, range iterator is an inner class, right? So every range iterator, every range iterator object has a reference to its enclosing range object. Right? So for a static class, that's not the case. Right? So we'll see that later on in the course. Right? Because the class is not static, though, that means that our range iterator, it always has access or it always has reference to the range that it's iterating over. The inner class object is able to access the fields of the enclosing class object, right? And so all that means is that our range iterator has access to the fields of its range object that it's iterating over, which kind of makes sense, right? If you have a range iterator that's iterating over the range 0 to 5, right, it needs to know that the minimum value of the range is 0, and it needs to know that the maximum value is 5, right? So in Java, the object has access because it has the iterator object has access to the fields of the enclosing range. Right? So what does the range iterator do? Right? Well, it knows how to count over a range. Right? So new range, so a range iterator over the range 0 to 10, right, knows it has to start counting at 0, right? And it goes up to, but not including 10. Right? So when you make a new range iterator object, right, it starts counting at the start of the range. Right? Every time you call next, right, the range iterator object goes to the next value in the sequence. Right? So again, if you have a range from 0 to 10, right, it starts at 0. If you call next on the iterator, it goes to 1. If you call next again, it goes to 2, and so on and so on and so forth. Right? When it gets to 9, right, the last value in the range, if you call next again, it throws an exception. Right? So the next method throws an exception if the iterator has finished iterating over the sequence of values. Right? If it hasn't finished iterating over the sequence of values, then it returns the current count and adds 1 to the count. Right? That method has next returns true if there's still more elements to visit in the sequence. Right? Otherwise, it returns false. Right? So if the iterator is done looking at every element in the sequence, has next returns false. If it's not finished looking at every element in the sequence, it returns true. Right? So when we implement the range iterator class, right, we need to provide an implementation of next, and we need to provide an implementation of hasNext. Right? So our class range iterator implements the iterator interface. Right? So the iterator is the thing that knows how to count over the sequence, right? So it needs to know what is the current count. So that's val. Right? When you make a range iterator object, it starts counting at the first element of the range, right? So it's going to set val to whatever the first element of the range is, right? And so that's start in the range object, right? Now notice that value start, it's not part of the range iterator class, right? It's part of the range class. So to get to that field start, you use this very strange syntax here, right? So it's the name of the enclosing class, followed by dot, followed by this, followed by dot, followed by start. Right? In this case, the this has to be there. Right? So this value is equal to the start value of the range that this iterator is iterating over. Right? How does hasNext work? So hasNext returns true as long as the value is less than the stopping value of the range. Right? Remember, the stop value is not part of the, when you count over the sequence, it doesn't count, the stop value, stop value is not part of the range. Right? So as long as the current value is less than the stopping value of the range, right, there's still more elements of the range to look at. Right? Again, to get to the stopping value of the range, right, it's the name of the class, followed by dot, followed by this, followed by the name of the field. So that's hasNext. Now what does next do? Right? So next returns the value of the iterator and then advances the iterator one position. Right? So next returns the current value and then increments this dot value. Right? So what is the current value? Well, it's just this dot value. Right? So I'm going to remember what that number is, and then I'm going to return it at the end of the method. Right? After I've remembered what the current value is, I can increment it by 1. Right? So add 1 to the value. Next should throw an exception if the iterator has visited every element. Right? How do you know if it's visited every element? Just call hasNext. Right? If hasNext returns false, then every element of the sequence has been visited, right? Throw an exception. The exception that you throw here is always no such element exception, right? So that's the standard exception that you throw, that is thrown when an iterator has no more elements to visit, right? And that's it, right? So the iterator, it's just a counter, right? That's all it is, right? It's counting from this start, going up to this dot, going up to but not including stop, right? Counts in increments of 1, right? So when you advance the counter, right, you just increment it by 1, right? And so in this case, the iterator is nothing more than it really is nothing more than just a counter, right? And it has these methods next and has next, right, that are specified by the iterator interface itself, right? Once you've implemented this class, right, so we've got our range, right? Inside range, we've got our iterator, right? Once you've done that, you can now write that little for loop here, right? So create a range object, right? The range object implements iterable, so you can write a for each loop using a range object, right? And now that thing there prints out the sequence 0 through 9, right? And so there's your Python style for each loop. There's your Python style counting for each loop in Java, right? If you wanted to, you can soup up the range class, right, so that it counts in different increments, right? So in Python, you can write the range class. You can specify the step size that you take when you move from element to element, right? You can do the exact same thing here, right? So inside the range, inside the range class, right, you'd have start, stop, and then a third field, step size or increment or something like that, right? Inside the iterator class, right, every time you call next, right, you go up by the step size instead of by 1, right? But the change is really straightforward, right? So there's an example of creating a fairly sophisticated, well, at this point in the course anyway, a relatively sophisticated class that implements an interface, right, and actually does something useful. Right. Any questions so far? All right, so that's implementing an interface. What if you want to make your own interface, right? So to make an own interface, it's dead easy, right? You simply declare the interface the exact same way that you declare a class, right? Instead of using the word class, you use interface, right? And then everything is public in the interface, right? Even if you don't include an access modifier, right? If you use any access modifier other than public, the compiler will complain, right? So an interface describes the public interface of a type, right? So here's an example of an interface called printable, right? So a printable, the printable interface is the interface that objects can use if you want to print them to standard output. Notice that this says it's not a particularly useful interface. All right, so once you've made your interface, you just put in the methods that you decide should be in your interface, right? Again, all your methods are public, right? And now, because they have no body, they all end with a semicolon, right? So our printable interface defines the method print, right? So in other words, every object that implements the printable interface must provide a print method. Print simply prints something to standard output, right? And now you can take any one of the classes you've implemented so far and say that they implement the printable interface, right? So for point 2, right, you can modify the class so that it now implements printable, right? So point 2 implements comparable, and now it also implements printable, right? If your class implements more than one interface, you just separate the interface names with a comma, right? Everything is the same as before, except now we must provide whatever method was in printable, right? So that method's called print, right? And now you can see why it's not super useful, right? Because all you have to do to print something is just call system.out.println anyway, right? So there's no real point in calling print, right? You can just use system.out.print, right? But there is an example of a very simple interface. Right? All right, You also saw an example of an interface in the current assignment, right? So in assignment 5, is that true? Yes, in assignment 5, right, you've got the player interface to work with, right? The player interface is just a bunch of methods, right, that don't have any implementation. Every time you implement one of the 3 classes that represent players, right, you just provide a method, an implementation of each method. All right. So I guess from a computing science point of view, the place where interfaces really shine are when you implement data structures. Right? So this is going to be our first data structure in this course. It's going to be something called a stack. Right? Okay, so these are all examples of real-life stacks. Right? Stack of files, a stack of books, stack of pancakes. Right? Each one of these things has the notion of the top of the stack. Right? So that's the top, oops, come on. That's the top book of the stack. Right? So there's also a data structure that corresponds to a stack. Right? So you can have a stack of stuff. Right? In the data structure version of a stack, right, there's only 2 things you can do with a stack. Right? I can put something else on top of the stack, so that's called push. Right? Or I can take the element that's on top of the stack off, and that's called pop. Right? In Python, a Python sequence typically implements push and pop. Right? And so you can use a Python sequence as a stack. Right? So you might know there's a list push and there's a list pop method. If you try to pop an empty stack, that's an error, right? So in Java, we throw an exception. Okay, so this is what push looks like in a picture, right? So you start out with an empty stack, and this is going to be a stack of strings, right? So if I push the string A onto the stack st, right, then the stack ends up looking like that, right? There's the string A, right? The top of the stack is the string A. If you push a B onto the stack, right, you've now got a B, and then there's an A, right? So the top of the stack is the B, the bottom of the stack is the A. If you push a C, right, the C becomes the top of the stack, right? The B is now the second element in the stack, and the A is the bottom of the stack, right? The first element that we pushed onto the stack is the bottom element now, right? And then the D, and then the E. Right? And so this is a sequence of elements, right? Starting from the top, we have the E, then the D, then the C, then the B, then the A. Now to get the elements out of the stack, you pop them out, right? So to pop the stack, right, I'm going to remember what this E is, because I'm going to return the element back to the caller, and then I'm going to remove this box off the top of the stack. Right? So when you pop the stack, right, that returns the string that was on top of the stack, so S is E. Right? The element disappears, and now the new top of the stack becomes the next element in the sequence. Right? Pop it again, so you get the D. Right? So S is D here. Right? The new top of stack is C. Right? Pop again, S is C. Right? Pop again, S is B, and pop one more time, the S is the A. Right? Notice that the first element that went into the stack, the A, was the last element to come out. Right? Do I tell you anywhere here? I don't tell you. Somewhere, hang on, I'm just looking quickly. Okay, so a stack is sometimes called a FILO data structure, first in, last out. Right? Or LIFO, last in, first out. Right? And it turns out these things are used, very widely used in computer science, so in algorithms, and in hardware, right? And they also show up in computer engineering. Right? If you ever use undo redo in a program, so PowerPoint or Word, right? You type something in Word and then you decide that's not what I wanted to type, you undo it, right? That's actually implemented using a pair of stacks, right? So whenever you do something in the program, right, that gets translated into some object that represents the thing you just did, and that gets pushed onto the undo stack, right? If you undo, right, it pops that command off the top of the stack and then looks at how to undo that command. Right? They're widely used in parsing, so any program that needs to read I guess text, I guess for our purposes, right, is a parsing type program, right? So your Java compiler has to parse your Java code, right? It has to read your code to understand what it's trying to do, right? Stacks are widely used in these parsing algorithms here. There's something called a call stack that keeps information about the active methods in a Java program. So whenever you call a method in Java, that conceptually that method gets pushed onto a call stack. If that method calls another method, the method that it calls gets pushed on top of the call stack, and so on and so on and so forth. Right? And that's how you can convert a recursive method into a non-recursive one. Right? So you can take a recursive method and turn it into an iterative method, right, by emulating the call stack of your program. Right? All right, so to illustrate an example of how to use a stack, right, so this is not useful. It's not super useful. It's silly, and it's inefficient. Right? But you can use a stack to reverse a sequence. Right? So I can reverse a list, returning the reversed list. Sorry, I can take in a list and return the reversed version of the list by doing the following. Right? So I'm going to make a new empty list that represents the list T in reverse. Right? I'm going to make a stack, a new empty stack. Right? And all I'm going to do is I'm going to take the elements in the list T and I'm going to push them onto the stack. Right? So for every string in T, push the string S onto the stack. Right? And now I'm going to reverse the process. So while the stack is not empty, I'm going to pop the stack. Every time I pop the stack, I'm going to add the popped string to my result, the reversed list. Right? And I claim that that reverses the sequence T, putting the reverse sequence into result. Right? So here's a picture of what's going on. There's my list. Right? I'm going to iterate over the elements in the list. Right? So every time in every iteration, I'm going to push the element onto the stack. Right? So first loop iteration, we take the A, push it onto the stack, then the B, right? And then next the C. Right? So notice that the elements of the stack from top to bottom are the reversed elements of the list. Right? So now I can just pop the elements off the stack and add them to the result over here. Right? So pop the C, put it in the result. Pop the B, put it in result. And pop the A and put that in result. And there's your reversed list. Right? You shouldn't do it this way. Right? The reasons you shouldn't do it this way is because you have to make a new stack. Right? And then you end up pushing all the elements onto the stack. Right? So to reverse this list T, I had to make an auxiliary data structure, right, that holds a copy of all the elements of T. So I've just used twice the amount of memory that I needed, right? And I've used one loop iteration to copy all the elements of T into the stack. And then I'm going to use a second iteration over all the elements to put the elements into the resulting list, right? You can reverse that list just by iterating over the sequence once. Right, so this iterates twice, and it also makes a second data structure. Right, so this is not a good way to do this. Right, but it does show you how a stack works. Right. Okay, so we want to implement this stack. Right, now notice that stack. If you pay close attention to this picture back here, that stack there. Right, if you turn it 90 degrees, it looks exactly like that list there. Right. So imagine rotating this that way, 90 degrees, right? It looks exactly like that list T. So you can think of pushing an element onto the stack. That looks a lot like adding an element to the end of the list, right? And popping an element from the top of the stack, that looks a lot like removing an element from the end of the list, right? And so you can actually implement this thing using a list. Right, so here's my stack class. Internally, so this is going to be a stack of strings. Right? Internally, it's just a list of strings. Right? This should look familiar to you, right? Because on your previous on assignment 5, right, you had a set of strings, internally, it was just a list of strings, right? So I'm playing the exact same trick here, right? Our constructor simply makes a new list, right? Hopefully in your string set, you made a new list, right? For the size, you simply return the size of the list. Okay, so what does push do? So push takes in a string, it adds the string to the end of the list, right? So this stack add the element, right? What does pop do? It removes the last element in the list, right? What's the index of the last element of the list? The size of the list minus 1, right? Notice that remove throws an exception if this index is invalid, right? So that's nice too. We even get the exception for free, right? In this implementation here, pop always runs in O1 time, right? Adding an element to the end of a list usually runs in O1 time, but every once in a while it runs in ON time, right? And we're going to see shortly, probably in the next lecture or two, right, exactly why this sometimes runs in ON time. Right? So there's your stack class implemented in a few lines of Java, right? It's not hard to do, assuming you have access to this list to the array list class here. Right? Now, there's at least 2 other ways to do this, right? And there's probably more. Right? So instead of using an array list here, I could just use a plain old array, right? So I can use a plain array of string, right? Now, if I use an array of string, right, I don't have access to that add method, right? So if I add to a full array, I need some way to make a new array and copy the elements into the new array, right? So we have to handle the reallocation of the array when the array becomes full ourselves, right? Or you can use what's called a linked structure, and we'll see this in a couple of lectures as well, right? Now all of these things, so you've got at least three different implementations of a stack, right? They all have their own distinct disadvantages and advantages, right? So what you can do is you can create an interface for a stack, right? So our interface is basically going to have a push and a pop method in the interface, right? You can then provide multiple different implementations of the interface, right? So I can provide a list-based stack, an array-based stack, and some kind of linked structure-based stack, right? And then I can let the user pick which one is most appropriate for their purposes, right? And this is already what's happening in the Java standard library, right? So if you want to use a list, normally you just pull out an array list, right? But every once in a while, it might be more useful to pull out a linked list, right? If you want a set, right, normally you pull out a hash set. If you want a sorted set, though, you can pull out you can pull out a tree set, right? And the same thing for map, right? So by creating an interface, what you can do is provide a unified way of accessing the data structure, right? So it has all the methods in the interface, but you can provide multiple different implementations, each which have their own advantages and disadvantages. Oops, all right. So let's implement a stack. So the next thing we're going to do is implement a stack using a raw array, hopefully. Oh. Stacks. Oh, let's see. I just want to, do I want to do this now? All right, so I'm going to jump ahead to the slide 30 in the next deck. I'm going to come back either in the next lecture or the one after that and cover up and look at that other stuff that I just skipped over. I do want to show you, though, how to implement a stack using an array next. Okay, so we used an array list to implement a stack. Dead easy, right? Instead of using an array list, I want to use an array, right? And so if you look at that array list implementation, that basically tells you how to do this using an array instead, right? So remember that when you have an array, right? Arrays, they always hold a fixed number of elements, right? An array of size 5 always has 5 elements in it, right? Our stack has a variable number of elements in it, right? So I'm going to need a mechanism to keep track of how many elements are in the stack rather than using just the size of the array, right? Similarly, using a list, right? I can push as many elements as I want onto the stack, right? And the list takes care of allocating memory to hold all the elements, right? With an array, you've got a fixed number of elements. So we're going to have to do something special if we try to put more elements onto the stack than there is capacity in the array. All right, so instead of adding and removing from the end of the array, right, because we're going to keep track of which element of the array represents the current top of the stack, right? So I'm going to show you a bunch of pictures of what's happening here. Here. So inside of our stack class, we're going to have an array, right? And we're going to do a stack of int, so it's called an int stack, right? So we have an array of size 16, it looks like in this case, right? When you make a new empty array, a new empty stack, right? We want to make that array. The values in the array aren't important, right? So this has all zeros in it, but that's just because that's how Java does it, right? We want to keep track of where is the top element of this stack, right? So top index is the index in this array corresponding to the top element of the stack, right? Notice it's set to -1, right, which is not a valid index. So that's indicating that there are no elements in the stack. Right? So if I push an element onto the stack, right, so I'm going to push a 7, right, what we're going to do is we're going to write into the first available array location, right? That's going to be top index +1, right? So we're going to set top index to 0, and then write into that array location the element that was pushed, right? So the 7 appears here, right? The top index is now 0, right? If we push again, right, we're going to take the top index and add 1 to it, right? So it becomes 1. And then I'm going to write the -5 into the array element at index 1, right? To pop an element from the stack, right, we're going to get the value at the current top index, and then we're going to make the top index go down by 1, right? So push the 7, push the -5, so we have 7 and -5, right? To pop the -5, right, we're going to remember we have the value -5 and return that, and then you're going to decrease the top index by 1, right? So top index goes down to 0, right? If you pop again, right, we're going to remember to return the 7, and the top index will become -1, right? So whenever you push, right, top index goes up by 1. Whenever you pop, top index comes down by 1. Yes, question? Yeah, no, we're gonna have to implement this ourselves, right? That's the whole point of all this. Okay. So our int stack class, right? All that it has internally is an array of int, right? And it also needs to do some bookkeeping, right? It needs to remember what element corresponds to the top, what index in the array corresponds to the top element, right? So we have a top index and we have the array. When we make the array, we have to decide how big an array are we going to make. So we're going to start out with an array of size 16. Right? So we're going to call that the default capacity. Where's the constructor? Sorry. I'm just... oh, okay. I guess we didn't... I guess I will show you the constructor in Eclipse. Where's my linked stack? Oh, here it is, array stack. Okay, so we haven't done it yet, but we're going to make a stack interface. Right? We're going to make a class called array stack that implements the stack interface. I guess this is a stack of string, but it's the exact same idea. So inside the constructor, right, remember what the constructor has to do? It has to set both of your it has to set all the fields of your class, of the class, right? So you're going to make an array, and you're going to set top, right? So we're going to make our array. For the int stack, it's new int, array stack dot default capacity, right? And the top value gets set to -1. Right? Okay, what about pop? Right? So for the pop method, right? Remember what we're going to do, right? We push the 7 and the -5 onto the stack, right? We're going to remember what is the value -5, so that's the value at the current top index. We're going to make the top index go down by 1. Right? So get the element at the current top of the stack. Right? That's just the element at top index. Right? Adjust the top index of the stack so that it goes down by 1. Right? And return the element. Right? Notice back here, if the stack is empty, we throw an exception. Right? And that's pop. So what about push? Okay, so push is slightly more complicated, right? If the array is not full, push is easy, right? You just increment top index by 1 and then write into the array index, right? So this is the state at which you can safely do one more push, right? So we've got 15 elements on the stack, right? I've got room for one more element, right? Okay, so, right? I have room for one more element. So how do I know I have room for one more element? Right? The top index, right, which is 14, right, is less than the size of the length of the array, which is 16, -1. Right? So the top index is less than my length of my array -1. Right? So if there's room, just increment the top index by 1. Right? So if I want to push another element onto the stack, top index becomes 15, and then I write into that element. Right? Top index goes up by 1, write into the element, write into the top index. Right? Okay, so what happens if I don't have space? Right? So in other words, what happens in the else part here? Right? Okay, so if you run out of space in the array, right? In this case, we would like to expand the size of the current array, right? So I want to let the user push as many elements as they want onto the stack, right? So if we run out of capacity in the current array, we need to make a new array that has bigger capacity, right? We then need to copy all of the old array elements into the new array, right? So I need to add capacity to the existing array, right? When we add capacity to the existing array, we have to decide how much more. Right? So how much more capacity do you add to the array? Well, I have to add at least one more element. Right? But it turns out you don't want to do that. Right? It turns out you want to do something else. So, else, right? We've run out of space in the current array. So I'm going to make a new array called new array. Right? When I make the new array, I'm going to make it equal to the length of the old array times 2. So in other words, I'm going to double the capacity. Right? If you increase the capacity of the array by 1, right, that lets the user push one more element onto the stack. Right? Then, if they push another element onto the stack, you've run out of space. So you increase the size of the array by 1, and then they can push one more element onto the stack. Right? Notice every time when you make this new array, you've got a loop that copies all the old elements into the new array. Right? So every time you end up in the else part here, right, you end up paying a price of computational complexity O(n), where n is the number of elements in the stack. Right? I have to copy all the existing elements into the new stack. Right? If I increase the capacity by 1 every time you add an element to the stack, you're paying another price of O(n). Right? If you double the capacity of the stack, right, I can now add n more elements to the stack before I have to resize the array again. Right? So this trick of multiplying the stack by 2 or any value bigger than 1 allows the stack to have, on average, O1 complexity when you add an element to the stack. Right? It's almost always O1. Every once in a while, you pay a price of On. Right? So technically, this is called an amortized complexity of O1. Right? But that's why we're doubling the capacity here and not adding 1. Right? Copy all the elements into the new array. And now don't forget to set this ARR so that it refers to the new array. Right? Now that we've got our new array, I can just push the element onto the stack. So I can recursively call push. Right? When you recursively call push, right, you fall into the, where's push? You fall into the if part here. Right? So increment the top index by 1 and then add the element to the current top index. Okay, so it turns out that in Java anyway, if you're working with raw arrays and you want the array to grow to accommodate more and more elements, you end up doing the same thing over and over and over again. There's a method that does all of that for you. Right? So arrays copy of will create a new array and copy all the elements of the old array into the new array for you. Right? So you can replace all of that with that. Right? So call copy of copies that array into an array of that length, returning the new array, right? Returning a reference to the new array. Right? So all of that stuff that used to be here can be replaced with one method called there. Right? And that's how you implement an array-based stack. Right? I'm actually over time, so I guess we have to call it quits there.